Acids and bases can vary in strength, and this is our first taste of the idea that chemical reactions don't always go 100% to completion. That's typical of precipitation reactions, not so for acid-base reactions. For strong acids and bases, though, there's complete reaction with water to give 100% hydroxide, and we can treat these using stoichiometry, all the tools of stoichiometry that we'll learn over the next few videos. To show the complete reaction of a strong acid or base, we just use a forward arrow like this. Weak acids and bases react only partially with water. This means that no matter how long we wait, all of a weak acid will not be consumed when it's dissolved in water. We'll have some weak acid left, even at very, very long reaction times. And we represent that by illustrating that both the forward reaction and the reverse reaction take place to an appreciable degree. And we can talk about the forward reaction as being incomplete. It doesn't go all the way to completion. It doesn't go 100% to completion. Not all of the acid is consumed, even at very, very long reaction times, pretty much no matter what we do in terms of weighting or cranking the temperature or anything like that. We'll have some reactants and some products left over. We're not going to worry so much about identifying whether an acid is strong or weak at this stage, but it's a great context to introduce the idea that chemical reactions don't always go to completion, and you'll see these two different types of arrows used in chemical equations to represent complete reactions versus incomplete reactions. Acids neutralize bases. This is a very important general principle. Acids and bases react with each other to produce a salt and water. And this very general chemical equation is meant to depict this process for a hypothetical acid HX and a hypothetical base that's a hydroxide source MOH. So it's a combination of a metal with the hydroxide anion, metal cation, hydroxide anion. We can split each of the reactants up into its component ions. And when we do this, I think it helps us see how the ions combine to form the products. The M plus and X minus ions combine, or they may actually just be spectators in many cases, to form the salt M plus X minus on the product side. H plus and OH minus combine to form an actual covalent bond, to form the small molecule water. And so there's absolutely a change in state that happens there. And if we list the state designators here, typically we'll have the acid and base dissolved in aqueous solution. The salt will remain dissolved in that aqueous solution, and the water produced will be a liquid in these neutralization reactions. So this depicts the idea that acids react with bases to form a salt and water. Let's dive into this idea a little more deeply by looking at an example problem. Here we're tasked with identifying the acid and base in a neutralization reaction, and the complete molecular equation is given to us here. It's the reaction of magnesium hydroxide, which is this, and hydrochloric acid, which is this. Now, based on the names alone and the fact that the magnesium hydroxide contains OH minus and HCl is named hydrochloric acid, we can pretty straightforwardly identify the acid and base. I think it also helps here to split out the compounds into their component ions. HCl, although not an ionic compound in the gaseous state, does form hydronium and chloride ions when dissolved in water, so we can think of it as an ionic compound. This makes it pretty clear that the magnesium hydroxide is the base and the HCl is the acid, and H plus and OH minus combine to form the water product shown on the right-hand side in this reaction. The magnesium 2 plus and Cl minus ions remain in solution and form aqueous magnesium chloride, we might say. If we were to actually write a net ionic equation for this process, though, the net ionic equation, realizing that the magnesium and chloride ions don't really do anything. They start out aqueous and they end aqueous. The net ionic equation for this process looks like aqueous H plus and aqueous OH minus going to liquid H2O. Let me actually add that aqueous phase designator here, aqueous OH minus going to liquid water. And this is actually true of all Bronsted acid-base reactions. Their net ionic equations look like this. And this is a common type of problem, identifying the acid and base in a neutralization reaction and thinking about how they combine to form the products. Let's work through a couple of examples of writing balanced equations for acid-base reactions based on textual descriptions. So in A, we have the weak acid hydrogen hypochlorite reacts with water. Well, hypochlorite we've actually seen previously as the OCl or ClO minus anion. So hydrogen hypochlorite is simply that anion paired together with H plus to make HOCl. And that's an acid. The text essentially tells us that, indicating that water acts as the base. Now, based on our prior definitions of what makes an acid and what makes a base, we can conclude that HOCl is going to donate a proton or give H plus to H2O. That means our products are OCl minus, the hypochlorite anion, and H3O plus. And because the acid was identified as weak, we're using reversible arrows here, showing that the reaction will not go to completion. In B, we've got barium hydroxide reacting with nitric acid in aqueous solution. And although it's not indicated, nitric acid is a strong acid. So we're going to be looking at a complete reaction here. The barium hydroxide combines with 2 equivalents of nitric acid to ensure things are balanced. Hydroxide inside the barium tells us it's going to be the base, and nitric acid, the name of the acid, tells us it will act as the acid, and we're going to transfer a proton from the HNO3 to the barium hydroxide, realizing that that proton is really going to end up in the linked to the OH minus oxygen. And so we end up with 2 equivalents of water, or 2 molecules or 2 moles of water, and 1 molecule or 1 mole of barium nitrate, BaNO3, 2. And lastly, I'll just mention for both of these examples the phases involved. Everything's aqueous except for water. So we're talking about a reaction taking place in water involving dissolved solutes. The only time a different phase pops out is when we make or use a water molecule in these reactions. In an oxidation-reduction or redox reaction, electrons are transferred, and that's the key. 2 molecules come together and 1 or more electrons is transferred from one to the other, molecules, atoms, or ions. And electron transfer can be full or partial. In your introductory chemistry courses, we'll look at full electron transfer. When you get to organic chemistry, if you go on and take that, partial electron transfers are common, which we still refer to as oxidation and reduction. Oxidation is defined as the loss of electrons, and reduction is the gain of electrons. Leo says Ger is a mnemonic that you've probably heard to remember this. Losing electrons is oxidation, gaining electrons is reduction. And in any redox reaction, we can identify oxidation and reduction processes, what are called half reactions. They're called half reactions because oxidation and reduction always come together. Splitting a redox reaction in half gives the oxidation and reduction half reactions. So for example, in this reaction, solid sodium metal is combining with chlorine gas to form solid sodium chloride. And so what's happening here in terms of charges is we're going from solid sodium metal, which is basically neutral sodium atoms, to sodium plus cations. That corresponds to an oxidation process, and here's a half reaction that represents it. An electron is liberated from the sodium atom, or given away or lost, and it becomes the sodium cation as a result. So that's oxidation. Losing electrons is oxidation. On the other side, the Cl2, which is more or less neutral chlorine atoms in the chlorine molecule, becomes Cl minus. And so the Cl atoms are gaining electrons. Cl2 is gaining 2 electrons to form 2 Cl minuses, and this is a reduction process. So oxidation-reduction reactions are characterized by these kinds of changes in charge due to the transfer of electrons from one molecule or atom or ion to another. To keep track of the changes in charge that happen in redox reactions, we make use of oxidation number, and oxidation number is the charge that an atom would possess if it were involved in only ionic bonds. So for ionic compounds, especially monatomic ionic compounds, where we've got just 2 atoms involved, sodium chloride, sodium fluoride, lithium oxide, oxidation number is very straightforward. It's the charge of the ions. Gets a little more complicated when we start talking about polyatomic ions and molecules, though. And there's some rules for oxidation number that we're going to lay down here so that we can assign oxidation numbers to certain classes of atoms and molecules. The oxidation number of an atom and an element is 0. So the elemental form has 0 oxidation number of each atom. For a monatomic ion, kind of analogously, the oxidation number of a monatomic ion is equal to its charge. So for sodium plus, it's +1. For chloride anion, it's -1, etc. Here are a few rules for common nonmetals. Hydrogen has an oxidation number of -1 when it's combined with a metal in something like sodium hydride. But when it's combined with a nonmetal, which is, I would argue, more common, it has the oxidation number +1. Oxygen very, very commonly has the oxidation number -2 in combination with both metals and nonmetals. And there was actually a mistake on the slide initially that I've erased and covered over. More or less, oxygen you should think of as having the oxidation number -2, except in very exceptional circumstances. The halogens, fluorine always has the oxidation number -1, and this is because fluorine loves electrons more than any other element on the periodic table. For the others, -1 is very common in combination with nonmetals, but we see +N when that element is linked through N bonds to oxygen atoms. And that'll come up in things like chlorite, hypochlorite, perchlorate, etc. These polyatomic ions with halogens at the center, the halogen often formally has a positive oxidation number. For a molecule as a whole, like a polyatomic ion with a net charge, the sum of the oxidation numbers of all the atoms must equal the charge on the molecular ion. And this is something that follows from the way we define oxidation number. Let's practice assigning oxidation numbers to the 3 compounds that you see here. And remember, an oxidation number can be assigned to each atom within the structure. So we'll want to assign an oxidation number to every atom that we see. In H2S, sulfur is a nonmetal. This means each hydrogen atom has the +1 oxidation number. Because the molecule as a whole is neutral, this means that the sulfur must have an oxidation number of -2, so that the sum of all the oxidation numbers is 0 in this molecule. In SO3 2-, well, we know that the oxygens each have an oxidation number of -2. That's a total of -6. And because the ion has a -2 charge overall, the oxidation number of the sulfur must be +4. If we add up all of these oxidation numbers, we get -2 overall, which matches the charge of the anion. For Na2SO4, each of the sodium cations in this ionic compound has a charge of +1, and the 4 oxygens, each of those has a charge of -2. Now, the overall compound is, again, neutral, and so we have +2 for the sodiums and -8 for the oxygens. This means that the oxidation number of the sulfur must be +6, so that the sum of all those oxidation numbers is again 0, since the molecule as a whole is neutral. Balancing chemical equations for redox reactions can get a little bit tricky, because in addition to the things being oxidized and reduced, we often have acidic or basic conditions that involve hydronium, or H+, hydroxide, OH-, or water, H2O, as reactants or products. But there's a process here for balancing aqueous redox reactions. We start by writing the 2 half reactions for the oxidation and reduction processes, and these will be clear from the parameters of the problem. We then balance all elements in those half reactions individually except for oxygen and hydrogen. We balance oxygen by adding H2O molecules on the reactant or product side. We balance hydrogen next, after balancing by oxygen by adding H2Os. This is going to introduce some hydrogens. We balance those hydrogens by adding H+ commonly to the other side from the one where we added the waters. We then balance charge by adding electrons to the half reactions, and one of them will include electrons on the reactant side. That's your reduction half reaction. The other will include electrons on the product side, and that's your oxidation half reaction. We then scale the 2 half reactions so that those numbers of electrons match, basically saying that if my oxidation is going to involve losing X electrons, my reduction has to involve gaining X electrons in order for things to balance overall. We then add those two together and simplify by removing species that appear on both sides of the equation, kind of spectator species that have been introduced by virtue of this process. So that's a long process, and we'll look at an example of this here shortly. A redox reaction happening in basic solution can be balanced by following the acid process and doing a few additional steps to essentially replace the acid H plus or H3O plus with hydroxide. So the first step to this process is to balance the reaction as if the reaction is taking place in acid by following the steps on the previous slide. We then neutralize the H plus by adding OH minus ions to both sides of the equation, equal numbers of OH minuses, so that we're not really changing fundamentally the nature of the reaction, we're just neutralizing the H plus since we're under basic conditions as specified by the parameters of the problem, right? Once we've done that, we take the H pluses and OH minuses and combine these to make water molecules, leaving no H pluses behind, right? If there are any H pluses remaining, we need to go back to step 2 and add more hydroxides. At this point, we may have redundant water molecules with waters on one side and the other, and we can remove any water molecules that show up on both sides of the equation to simplify. And that's the last step here. And if you follow this process, you'll be left with only hydroxide and water in addition to the reduced and oxidized species on the reactant and product side for a redox reaction taking place in basic solution. Let's practice balancing a redox reaction in acidic solution. And here we're looking at the reaction between dichromate ion, we'll see that structure in a second, that formula, and iron 2 to yield iron 3 and chromium 3 in acidic solution. Acidic meaning we're going to have H plus and water molecules around on our reactant or product sides. So first, let's write the half reactions. Dichromate is Cr2O7 2-, and dichromate to chromium 3, on the product side we have Cr3+, that's the chromium 3 ion. Iron 2 is Fe2+, iron 3, Fe3+, so pretty straightforward half reaction there. Our next step is to balance all atoms that are not hydrogen or oxygen. And the one thing that looks off here is the number of chromiums. We've gone from 2 to 1. So we need to add a 2 before the chromium so that our chromium atoms balance. The other half reaction is already balanced. Next, we balance oxygen. And we do this by adding the appropriate number of water molecules opposite where we see oxygen. So we have O7 on the reactant side, so we'll need 7 water molecules on the product side. Those 7 water molecules introduce 14 hydrogens, and in the next step, we balance on hydrogen by adding H plus to the other side, 14 of them. So the charges and the numbers of atoms are getting crazy, but rest assured, we're still balanced overall on number of atoms at this point. And in fact, we've accounted for all of the atoms, chromium, oxygen, and hydrogen, in this first half reaction. Don't need to do a thing to the second half reaction because no oxygens or hydrogens are around. What do we do next? Well, now we need to worry about the charge. And to deal with the charge situation, we add up all the charges on the reactant and product sides and looked for any difference. On the reactant side here, we've got 14 pluses and 2 minuses for a total of plus 12. On the product side, we've got 2 times 3 plus for a total of plus 6. So we need to add 6 electrons to the reactant side to account for this. And I've drawn those in green here. In the second half reaction, the charges don't balance either. We go from plus 2 to plus 3, and in order to make the charges balance, we have to add a negative electron on the product side so that we have plus 2 overall here and plus 2 overall here. So now our charges balance. We're almost ready to add the oxidation and reduction half reactions together. We just have to scale them so that their numbers of electrons match. Specifically, we've got to take this second reaction and multiply everything by 6 before we add them together. And actually, before we do that, it's worth noting that we've identified now that the chromium, the dichromate to chromium 3 is the reduction process, and the iron 2 to iron 3 is the oxidation process, and we can tell that based on where the electrons show up on the reactant side or product side. So next, we're just about done. We just need to add together the scaled half reactions, and this is what we end up with. Cr2O7 2 minus, 6 Fe2 pluses, because we multiplied by 6, 14 H pluses from the first half reaction. The electrons cancel, and so we don't write those. 2 Cr3 pluses, those came from here. 6 Fe3 pluses coming from 6 times this, and then 7 H2Os, which came from the first half reaction again. And this is our overall balanced equation for this reaction occurring in acidic solution. Let's balance the same reaction now in basic solution. And where I'm going to start is with this acid balanced equation that we generated on the last slide. So this is the same equation that we saw previously. To generate the basic version of this, the basic version, we're going to first add a number of hydroxides equal to the number of H pluses that we see on both sides. So 14 OH minuses on both sides. The 14 H pluses and OH minuses over here will combine to form 14 waters. And I've listed that here, leaving everything else the same and just folding in the 14 OH minuses into our list of products over here. Now we see we have 7 waters on the product side and 14 on the reactant side, and so we can subtract out 7 of the waters to leave us with 7 waters on the reactant side and none on the product side, leaving us with our overall balanced equation. Dichromate, one of those, plus 6 Fe2 pluses plus 7 waters goes to 2 chromium 3s, 6 iron 2s, and 14 hydroxide molecules. And it's the presence of the water and hydroxide that points us to this being a basic reaction, a reaction in basic solution. And I would encourage you again to make sure that all of the atoms and the charge are balanced in both this reaction and in the acid balanced reaction that we looked at previously as well.